Okay, so in this slide, we are going to show how the acid-base reaction occurs and use arrows to draw the conjugate acid and the conjugate base that are formed from this acid-base reaction. So the first thing that you're going to do is ask yourself, what is going to act as a base and what's going to act as the acid? We have an ionic compound here, NaNH2. So we first draw the charges. Na is plus and NH2 is minus. That's clearly going to be our base in this reaction. So the NH2 minus is going to act as a base. Then we need to find what's the most acidic proton on the alkyne. The most acidic proton on the alkyne is attached to the sp carbon of the alkyne. So it's a terminal alkyne, it has an sp carbon, and the hydrogen attached to the sp carbon is the most acidic proton on the alkyne. The base grabs the hydrogen from the most acidic proton of the alkynes. The arrows in an acid-base reaction go from the base, which is a lone pair of the base, grabs the hydrogen from the acidic proton, and the CH bond breaks and gives the electrons move it on top of the carbon, the sp carbon. So once you have drawn the arrows, you can now just follow the arrows to draw the products of the reaction, which would be the salt of the alkyne. Make sure you count your carbons. You started with 5 carbon, so you would have 5 carbon alkyne, but now it's the conjugate base of the alkyne and is often called the salt of an alkyne. The Na plus now associates itself with the anion, so you draw that near the anion, and in the process NH2 minus grabbed a hydrogen to form ammonia, NH3. So once you draw your arrows, it's very easy to draw the products that are formed from the acid-base reaction. That's the first part of this problem, to show arrows and draw the conjugate acid and the conjugate base of the reaction. So let's just write which is the conjugate acid and the conjugate base in this reaction. We started with an alkyne, which was the acid. So the conjugate base is the salt of the alkyne, and ammonia is the conjugate acid. In this reaction. Alkyne was the acid and NH2 minus was the base. So once we have the first part of the problem, the next part is to find the direction of equilibrium in this acid-base reaction, which basically means we would like to know if this reaction moves forward, if it gives you the conjugate base and the conjugate acid. The way to do that is to find the pKa's of the acid and the conjugate acid that are formed in the reaction. The pK values are listed here. You can see that terminal alkynes have a pK of around 25. So we write that the pK of the terminal alkyne is 25. pK of ammonia is listed here as 38. As you remember, higher pK means a weak acid. So ammonia is a weaker acid in this reaction. Equilibrium always moves towards a weak acid because if ammonia is a weak acid, its conjugate NH2 minus is the stronger base. Is the stronger base in this reaction, which means that the equilibrium will move forward and we should pick A as the right arrow. There's a big difference in pK, 25 to 38, equilibrium moves forward. So just to summarize, NH2 minus is going to act as a base in this reaction, grab the most acidic proton from the alkyne, which is attached to the sp carbon of the alkyne. The conjugate base is the salt of an alkyne, and the conjugate acid formed in this reaction is ammonia. To find the direction of equilibrium, we look at the pKs of the acid and the conjugate acid. Equilibrium always moves towards weak acid. In this case, ammonia is a weaker acid than the starting alkyne, so we pick arrow A to show the direction of equilibrium.